Hopefully everybody can hear me and they're watching a video with sound. If not, hopefully they read that sign. This is the Chapter 4 in Geometry study guide on which we take notes. And this is lesson 411. And here we go. A couple definitions to start with. Interior angles on a triangle are pretty logical. They are the three angles in the inside corners. Now, an exterior angle is a little bit harder to define because, as you can see, these triangles are not drawn as typical triangles. The sides have been kind of extended outward. The reason for that is when we define exterior angles, we need those extensions. So an exterior angle would be that one or this one. They're essentially the angles that are on the side rather than right here. This is not an exterior angle, whereas these are. Also in this corner, this is not an exterior angle as it's defined in geometry, but these two are. A couple examples of exterior angles on this triangle. And finally, this corner here, this angle right here, is not an exterior angle, but these two are. So in this section, Chapter 4, Section 1, Part 1, we're talking about classifying triangles. And there's several different names that we can give triangles based on their classification. And they fall into two categories. One is looking at just how long the side lengths are on a triangle. Are all three of them different? Then it's called a scalene triangle. Are there two side lengths that match each other, but the third one does not? That's called isosceles. And then the third one is when all three sides match. That's called equilateral. So as you can see in our examples, this one has no sides that match. Nothing's been marked congruent, so that means all three sides are different. So that would be scalene. On this triangle, all three sides match each other. That would be equilateral. And on this one, there's two sides that match, but the third side does not. That is isosceles. The other way to classify triangles is to look at their angles and see how they compare. So, an acute triangle has three angles that are smaller than 90 degrees. A right triangle has one angle that's 90 degrees. An obtuse triangle has one angle that's bigger than 90 degrees. And if you look carefully, you can see this one right here would be more than a perfect corner if you went from one side to the other. So that's your obtuse angle. That little guy right there. And then finally, an equiangular triangle has all three corners that are congruent to each other. So I found that students have a harder time classifying triangles by their angles than they do with the sides. Most students can remember equilateral, isosceles, and scalene, but when it comes to the angles, it gets a little bit more challenging. So just remember, if you see all three corners the same, that's equiangular. If you see one right angle, that's a right triangle. And then the only other two would be looking for this obtuse angle. If you see one angle that's bigger than 90, that's an obtuse triangle. But if you don't see any triangles or any angles that are bigger than 90, all three of the interior angles are smaller than 90, then that's acute. So on this one, I see an angle bigger than 90 degrees. So that's an obtuse triangle. Here I see one angle that's 90 degrees. So that's a right triangle. And here I see two angles that are the same, but the third one is not. Well, that's not equiangular, is it? So that's out. Do I have an obtuse angle here? Do I have an angle that's bigger than 90 degrees? Well, these two would add up to 150 degrees, which means that the third angle would have to be 30 in order for all three of them to add up to 180, right? Well, I don't have an obtuse angle then. Nothing's bigger than 90. I certainly don't have a right angle. Nothing's 90 degrees. So by default, this triangle, since it doesn't fall in the first three categories as I read from right to left, it must be an acute triangle. Are all three angles inside less than 90 degrees? Yeah. So that's the category, acute. Now on the next page, I'm just going to do this example simply because these take a lot of time. So for this lecture, for this video, I'm just going to skip that one and then use the whole page for the top example. So, classify triangle RST by its sides. Okay, well, classifying by the sides, we have to know how long the sides are, right? We have to know if all three are different, two are the same, or all three are the same. So, the way that we find lengths when we're giving the points at the ends of a line segment, or line segments, because these are three line segments, 1, 2, 3, would be to use the distance formula. The distance formula says that if I subtract the y values, so 3 minus 2, and square it, and then subtract the x values, negative 3 minus 5, in the same order that I did the y's, left, right, and then square it. And if I add those two together and take the square root, I can find the distance between those two coordinate points. So let's see. I have the square root of 1 squared plus negative 8 squared, which gives me the square root of 1 plus 64, or the square root of 65. Now, the square root of 65 cannot be simplified any further, so we're just going to leave it the square root of 65. So the length of the side that runs across the top of the triangle is this many units long. We don't need a decimal approximation, we simply just need to know the root value for these types of questions. Another side length would be ST. So here we could go 2 minus negative 1 squared plus 5 minus 3 squared. Difference of y's, difference of x's, quantity squared. Alright, so we would have 3 squared plus 2 squared, and we would get the square root of 13. Root 13, again, just like the square root of 65, cannot be simplified any further, so we would just leave it as it is. And then finally, TR. TR, I'll subtract the difference of, I'll find the difference of the y's and then the difference of the x's, so it would be 3 minus negative 1 squared plus negative 3 minus 3 squared, which gives me 4 squared plus negative 6 squared. So I'd get 16 plus 36, which gives me the square root of 52. Now the square root of 52 you can simplify. You could break that down into the square root of 4 times the square root of 13, because 4 times 13 is 52, and you would get a simplified side length of 2 root 13. Okay, so RS and ST and TR have 3 different side lengths, which means that classifying it by its sides, it would be scalene. All 3 sides have different lengths. So that's my first answer, is scalene. Now, the second thing we want to do is determine if it's a right triangle. Now, basically what we need to do is figure out if there's any right angles. I definitely do not think that's a right angle, it's just too small. This one also does not appear to be a right angle. The only one that might be a right angle would be this one, right here, at corner T. So what I'm going to do is I'm going to figure out if side RT and side TS actually form a right angle. Now we've learned that if 2 sides come together to form a right angle, they're called perpendicular. And the slopes of 2 perpendicular lines, or in this case 2 line segments, if you multiply them together and the answer is -1, then it is a right triangle. If you multiply the slope of this line and this line together and you don't get -1, then that's not a right angle. So that's what I'm going to do. I'm going to find the slope of RT. So I would take the difference of the y's on the top, 3 minus -1, and the difference of the x's on the bottom, -3 minus 3, and I would get 4 over -6, which reduces, if I divide by 2, to 2 over -3. The slope of TS is, difference of the y's would be 2 minus -1, and the x's will be 5 minus 3. So, oops, I'm not on the screen. There we go. So we would find 3 over 2. Okay, so how do we know if these 2 lines are perpendicular, if they actually come together at a 90-degree angle here? Well, we multiply these 2 answers together. So if we multiply the slope of RT times the slope of TS, what number do we get? Well, this on the top would be 6. On the bottom, if we multiply straight across, it's -6. And then 6 divided by -6 is indeed -1. So sure enough, this corner right here is actually a 90-degree angle. And I could mark that like that if I wanted to. And that means that this triangle is a right triangle. So I'm going to say that it is both scalene, based on the side length comparisons, and right, based on the fact that I have one right angle present.